Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to talk about galvanic cells, which is just a fancy way of talking about an electrochemical cell that produces energy. Now, this is a very hot topic at the moment because we're always in search of new electrical energy sources. And a great way to store and use energy is through electrochemical cells. So galvanic cells essentially focus in on any sort of electrochemical cell which produces a voltage greater than zero. This means that we're putting extra energy into our flow of electrons, and we can capture some of this energy by hooking it up to things like electric motors, the electrical grid, or even just running it through a light bulb. So for all of these systems, again, since these electrons have excess energy, we can harvest that and drive these important physical processes. And any of these reactions that have a potential greater than zero are always said to occur spontaneously. So that would mean that if I would mix zinc and copper salts together, I would expect the reaction to spontaneously produce copper solid and zinc salts. And they're said to occur as galvanic cells. So these are energy producing cells when set up in an electrochemical cell system. So for example, let's go ahead and look at our copper zinc system we've talked a fair bit about, where we're using zinc to reduce copper salts down to copper solid. So in this case, this reaction occurs with a standard state potential of about 1.1 volts. This means that this reaction is quite favorable and can generate a fair bit of energy. Well, what does this mean when I'm mixing my zinc and copper salts? It means that this reaction will occur spontaneously and that we can hook it up into an electrical system as an energy source. And actually, this reaction I know seems a little bit kind of artificial. Why would I care about zinc and copper? Well, it turns out this made one of the first batteries in the late 18th century, which was more or less constituted by making a giant pile of zinc and copper discs. And so it turns out if you hook a wire up on either side of what's called a voltaic pile, it ends up generating a fair bit of energy. So each one of these cells produces about 1.1 volts of energy, which, I mean, honestly, we have very little context. But to put it in some context, a typical AA battery has a potential about 1.5 volts. So this means that this voltaic pile, each cell is a little worse than a typical AA battery, and much worse than a wall socket, which has about 110 volts, so about 100 times as much energy as a voltaic cell. Well, one of the things you can do if you look at electronics is you can increase a voltage of a system by stacking all of these cells on top of each other. Every time you double the size of the stack, you double the amount of potential produced. So you could end up using this voltaic pile to produce 110 volts by stacking up 100 of these cells on top of each other. A little unpractical, but very impressive for late 18th century Europe. And so it took the world by storm, and a lot of experiments in electricity took place afterwards. Now, it's worth noting that most of our voltaic and galvanic cells can be used in a very similar fashion as potential energy sources. Now, here's the question of how can we identify what a potential galvanic cell would be? Well, we can do this by using our table of standard reduction potentials. Because remember, anything that occurs near the top with a positive reduction potential, these are species that will produce a lot of energy when being reduced. If we go down, any of these systems with very low reduction potentials means they will produce a lot of energy when being oxidized. So what we can do is identify any potential galvanic cell by taking one of the reactions that occurs up high and designating that as a reduction reaction. For example, trying to reduce silver ions into silver solid. However, we would need a source of those electrons. So then we can go ahead and find a species that's lower to act as an oxidation source, such as as we'll see quite a lot, zinc solid is a very good reduction source because you'll notice it's towards the bottom. Once you get into any element below zinc, like aluminum, magnesium, sodium, calcium, potassium, or lithium, these are all fairly unstable and hard to isolate in the real world. So zinc is often used fairly frequently. And so we can identify any sort of standard cell potential just by taking these two reactions, taking the difference. If the top reaction is my reduction reaction, the bottom reaction is my oxidation reaction, it will form a galvanic cell. Make sure that you don't flip that, because if the forward reaction is spontaneous, the reverse reaction is unfavorable. So let's go ahead and put this into practice. Let's try and figure out what the potential would be for a galvanic cell made using lead and manganese. So in this case, I know I'm going to make use of lead, which is here with a potential of negative 0.13, and manganese, which is all the way down here with negative 0.118. So as a result, I know that I'm going to be reducing the species that is higher. So that's going to be my lead being reduced from lead salts to lead solid. And I'm going to be oxidizing the species that's lower down. So that's going to be manganese. Note that even though I'm writing the oxidation reaction, I'm taking great pains to show that this is the actual reduction potential. The reason I'm doing this is because then I can use the cell, calculate the cell potential by, again, doing the cathode, so the reduction reaction, minus the anode, again, the oxidation reaction. Do note that this equation only works if you're using both of the reduction potentials, and make sure that you don't mix and match the signs of the equation. However, doing this, we end up finding out that the overall cell potential is about 1 volt, meaning that I could make a galvanic cell using lead 2 plus anions and manganese solid and actually generate a fair bit of energy. Now, one of the important things here is you'll note that we're always here referring to just standard state potentials. And as we've seen before, changing the concentration of a reaction can actually change the signs quite significantly. So next time, we're going to be looking at how we can evaluate the potential of a system as we slowly change the concentrations. Until then, take care.